Swayam Prabha. Digital India. Educated India.
So, in the lectures that we have discussed so far, we have primarily looked at benzene. Now, we'll start looking at substituted benzenes. So, the first example that we're going to see is phenol, and this is going to be basically bromination of phenol. So, notice right away that this reaction produces not just one substitution, but actually it produces the tri-substituted product. So you get 3 bromines in the product. The second thing that you notice is that there is no Lewis acid. Okay, so no Lewis acid is needed. Okay, so this is important because that means that phenol is substantially more reactive when compared to benzene. So you may recall that for bromination we needed Br2 and aluminum chloride. So how do we understand these two results? That is, there is a bromination that is happening, but it's happening only in 3 of the possible 5 positions, and there's also multiple brominations. And the second result is that there is no Lewis acid needed. So they both are sort of related so we'll discuss that now. Okay. So let me just draw out an arrow pushing mechanism, and then we can sort of look at it in a little bit more detail. Okay. So the first thing is that phenol clearly is a electron donating group, although it's electron withdrawing by induction, but it's electron donating by resonance. So you can easily imagine that lone pair on oxygen can be sort of given away. Let me just number these carbons so that it's easy for us to follow. We follow the same pattern 4, 5 and 6. And so what could happen is that you have Br and then you have Br, right? So it attacks here and bromide departs, and therefore the product that you would expect would be, so I'm just going to keep the same 6-member ring here. There's a bond between oxygen and carbon, so there'll be O, H, and that results in a positive charge here. There's now a bond between carbon 2 and carbon 3. The bond between carbon 5 and carbon 6 remains the same. And carbon 4, which used to have only the hydrogen, now also has a bromine. Okay, so let me just do the numbering once again. 1, 2, 3, 4, 5 and 6. Okay, and there is a full positive charge on oxygen. All right, now you can propose that H plus is being lost, and this could be taken up by Br minus, for example, and there is a loss of H plus, and it happens in the following manner. So it can go back here, and this can go back there, and this restores the neutral charge on oxygen. So let me sort of work this out step by step. Here is so first H plus HBr is gone, so let's write that out, HBr. Okay, and the second step is that in carbon 4 there is Br, it still remains, and in carbon 3 and 4 there's now a double bond. Carbon 5 and 6 the double bond remains, and there's a new bond that's formed here, and this is my OH. Okay, so let me just number this 1, 2, 3, 4, 5 and 6. Okay, so this is how this reaction can occur, and this sort of makes sense from many angles. One is that the OH group is quite electron donating, through resonance, and so you can I don't see any problem in this mechanism the way it's written. Okay, now to understand the tri-substituted reaction, let me just redraw bromophenol, OH and Br, and so you have a electron withdrawing group by induction, and electron donating group by, we'll look at this a little bit more detail, but the phenol is still reactive enough, and so it can sort of now react with another mole of bromine, and this time it's going to attack in the following manner and kick out bromide, and we'll stick to the same sort of numbering schedule: 1, 2, 3, 4, 5 and 6, and so the product that is going to be formed, you keep the same aromatic ring or benzene ring, sorry, and notice that you have the OH being involved because the OH is now involved by resonance, and there's a new bond between this carbon and bromine, and I'm just writing out the carbon hydrogen bond. It was already there, and so the bond between 1 and 2 is broken, so 1, 2, 3, 4, 5 and 6. There's already a Br in carbon 4, and now the bond between 3 and 4 remains intact, the bond between 5 and 6 remains intact. Okay, so now if you have a Br minus or any other base attacking here, you can propose that this bond can break and the new bond is formed, and it goes back to the phenol. Okay, so let's carefully redraw the structure. So Br is here, Br is already here, and now your OH is restored, and just to complete the numbering, this is 1, 2, 3, 4, 5 and 6. Okay, so this is how the second bromine happens, adds in there's a substitution reaction. Now I will let you work out the details of the addition of the third bromine, and so the final product that you get would be OH, Br, Br and Br. Okay, so now it's useful now to sort of define these terms. So when one draws a benzene ring and it already has a substituent X, okay, so this position or these two positions are called as the ortho positions. Okay, and this over here is called the para position, and lastly these two positions as shown here are called the meta position. Okay, so therefore this ortho is basically, if I number the carbons, then the numbering would tell us how this happens. So 1, 2, 3, 4, 5 and 6. See, ortho is basically 2 and 6, meta is 3 and 5, and para is position carbon number 4. Okay, so in the case of bromination of phenol, we get the ortho and para substituted product, and you get the tri-substituted product. Now if you want to make the mono-substituted product of phenol, that is, you just want to make one substituted bromophenol, then what you can do is to reduce the temperature, go to temperatures which are like less than 5 degrees centigrade, and use solvents such as carbon disulfide, and the product that you get is 4-bromophenol. Okay, so this also tells us that the para substitution is more likely to be the first reaction that happens, because when you go to low temperature, it's going to give you this as the major product. You also get the ortho product, but it's minor. Okay, so therefore, if you want to make a mono-substituted product, you may have to go to low temperatures in this case of compounds which are highly reactive to electrophilic aromatic substitution. Okay, now we will spend some time and figure out why this, or how to understand this this directing ability. Okay, so what I mean by directing ability is basically so when you have a substitution X here, and if the product that you get, if I just look at statistics, then the ortho position as shown here has 2 hydrogens, and therefore there are 2 substitutions that are possible. Also, meta has 2 substitutions, whereas para has only 1 substituent. Okay, so therefore the ratio of ortho to meta to para purely by statistics should be 2:2:1, and all your reactions, if there is nothing else that determines the reaction outcome, the major 2 equally distributed products should be ortho and meta, and para should be the minor isomer. But in the case of phenol, you actually get para as the 85% yield product. So clearly there is something else that is going on other than just statistics. Okay, so now we'll try and understand what this process is, and the way we understand it is, let me again draw out phenol, and so this is the OH. Now what I'm going to do is I'm just going to draw some resonance forms. Okay, so when I draw the resonance form of phenol, so I have OH, a positive charge here, and now there is a full negative charge over here and over here. Okay, so let me just, for ease of understanding, let me just number these carbons. So this is 1, 2, 3, 4, 5, and 6. It's carbon 1, 2, 3, 4, 5, and 6. Okay, so if I have to draw the next resonance form, the way I would do this is to move this negative charge over here and move this over here. Okay, so this gives me the next resonance form where there's a double bond between carbon 2 and carbon 3. The rest of the molecule pretty much remains the same. Okay, and lastly, if I have to get here, so let me just complete the numbering. Okay, so lastly, if I have to get the one more resonance form as possible, so if I have to do that, I do it in the following way. Okay, so double bond OH plus remains the same. It's a bond between carbon 2 and carbon 3. There's a bond between carbon 4 and carbon 5, and now there is a full negative charge over here. Okay, so therefore, if you see the structures, the negative charge is localized in positions, in the resonance forms, in positions 2, 4, and 6. Okay, so here with the phenol, the negative charges are here, here, and here. Okay, as per the resonance forms. So it is not surprising that these positions are more reactive. So the electron density on these carbons is higher. Okay, and this results in increased reactivity of these positions. We'll also look at in more detail the energy profile at a later lecture, but this certainly contributes to the ortho-para directing ability of phenol.